So this next video, we're going to talk about aromaticity, right? We keep calling these things aromatic groups, right? Like benzene, right? Back in Orgo 1, for when we were learning functional groups, we were calling this a aromatic ring. And benzene is really just a type of an aromatic ring. And aromaticity has a particular kind of property that we'll be discussing in this video. But when we talk about aromatic compounds, they're really anything that have these characteristics. So a benzene ring is aromatic, and also some of these other derivatives. For example, right, benzene with a methyl group, right, toluene, that's aromatic. This other group here, a benzene ring with a double bond, styrene, this is also aromatic. Naphthalene that we learned about in the last video, also aromatic. All these compounds have aromaticity, right? Right now, it's obvious they look like benzene, they have other groups attached to them, they're still aromatic groups, but they have special properties. And something we've been addressing, and I think we mentioned in Orgo 1, is that when we have alkenes, and we do, for example, all these reactions we've done in Chapter 8, we do them on alkenes, like this bromination, for example, where we get this anti-addition of Br2 across the alkene. We can't do that reaction with aromatic groups, right? Even though, right, they're alkenes, the same reaction drawn above does not work. Okay, we can't get any bromination addition across the alkenes. That's because these benzene rings and aromatic groups in general, right? We should be saying benzene/aromatic rings are very stable. So we need different conditions to react them. Okay? And so why is that the case? And we'll see more of these reactions in the next chapter, but why is aromaticity such a big deal? And so it really comes down to the fact that these double bonds, you might have seen this structure in Orgo 1 or in your notebook or online looking at videos, is that benzene rings, these double bonds, are constantly in flux. Right? They do this sort of shifting here where they kind of go all around the ring. And so one way to abbreviate it, right, we have our resonance structures here. One way to abbreviate benzene rings, and you might have seen this in general chemistry or wherever else, is kind of just draw a circle in the middle. It's implying that these electrons, right, are in flux, they're always moving, and so that's why we kind of draw in this ring structure here, which is fine to do, right? If you want to draw your benzene rings like this from now on, totally fine, very acceptable. And it's because, right, this structure here is showing pi bond movement. All 6 electrons here, right, all 6 pi electrons are delocalized, right, which we know is great for resonance, and all are moving, right, they're all moving around the electron, the benzene ring. And moreover, right, this is important too, is because of this movement, right, all these carbons, right, all 6 carbons are sp2, right, they're planar. This is really important to aromatic rings in general, okay? The title here, and we might talk more about this in class, Kekule structure, that's referring to these individual benzene rings. Kekule is the name of the scientist who discovered the structure of benzene. We might talk more about that in class. The history of it is pretty interesting, in my opinion. We're going to skip this part. We've kind of already discussed it, right? Benzene is stable because of the reasons we've already mentioned, right? These influx electrons, right? These delocalized electrons. This next part here we will also skip. But this next part here we'll talk about very briefly. So, right, if you remember from our discussions of NMR, right, these aromatic groups, right, we said appeared around, right, aromatic AR. These aromatic protons appeared around 7 to 8 ppm. And the reason for that is because of the aromaticity of benzene rings. Right, if you notice, right, I've drawn a crude diagram here of benzene with all the molecular orbitals here lining up. This is kind of how it looks like in reality, where we have right, the kind of top here all stabilized, right? All these pi orbitals are overlapping, and on the bottom we have all of these lower orbitals overlapping, right? Like this, the top and bottom overlap. These are all these pi electrons, right? All these pi bonds here. Again, constantly in flux, right? And what's happening, right, in an aromatic system, in an NMR, is that the NMR, right, nuclear magnetic resonance, a magnetic field is being introduced to the system, right? So we're getting into a little bit of physics here. Not super important, but I think it's interesting. The magnetic field represented by B here, B naught, is introducing a magnetic field. And if you took physics, there's this property called Lenz's law that says that when we introduce a magnetic field, electron current, right, or electricity, will flow in the opposite direction to make an opposing magnetic field. So this hydrogen here, right, kind of drawn off to the side, is getting hit by the magnetic field, right, which is what essentially makes protons show up in an NMR spectrum. Normally, right, hydrogens appear, right, lower on an NMR, but when we have an aromatic compound, again, because of this magnetic field, what's happening here is that the electrons are opposing the current. So we end up having this situation where the electrons themselves, because of the way they're flowing, are making an opposing magnetic field, right, with these arrows here kind of showing an opposing magnetic field. So what happens is the protons are getting hit essentially with a secondary magnetic field generated by benzene. We can talk more about this in class. It's not super relevant, but that's why these protons show up more downfield than they would normally, right? Because these normal alkyl groups, right? If we just had a normal propane, right? These hydrogens show up more like around here, right? Versus with benzene rings or aromatic groups that have this magnetic property. Anyway, that's not the most important, but I think it's interesting. Anyway, so the aromatic character of compounds are defined as this, right? When we have aromatic compounds, we have the following characteristics. They are stable, right, like we mentioned. They undergo substitution, not addition, which we'll talk more about in chapter 17, right? So we're not going to get things adding across alkenes like we saw in chapter 8. They have a ring current, right, which makes a downfield shifting. And they're planar with equivalent carbon-carbon bond lengths, meaning, right, if we have this situation here, right, alkenes actually have a shorter bond length than alkanes, right? So alkanes have a longer bond length. But in a benzene ring, right, even though it looks like we have, right, covalent bonds and pi bonds around the system, right, because they're in flux, all of these bonds here are of equal length. And criteria for being aromatic, we have the following rules here, okay? So these are characteristics. What do we need in order for them to be aromatic, right? They have to be cyclic, okay? That's a big rule. They have to be conjugated, right? All those double bonds have to be in a row. They have to have something called 4n plus 2 electrons, which is something called Huckel's rule, where they need 4n plus 2 electrons, where n is any integer. So for a benzene ring, right, this has 4n plus 2 electrons, because when n equals 1 plus 2, we have 6, right, which is how many electrons a benzene ring has. And they have to be planar, which this benzene ring is, right? We talked about the planarity of benzene rings before. But we can have different compounds as well that can also be aromatic. We can have something like this system, for example, where we have a 5-membered ring with a lone pair on that carbon. We still have our 4n plus 2 rule applying here, where we have 6 electrons, right? And we know that this carbon here, right, is sp2 hybridized because it's conjugated with the rest of the carbons, right? It's next to these double bonds. It's planar, it's conjugated, has 4n plus 2 electrons. This compound is also, right, aromatic. So we're going to look during class at more examples here of aromaticity. And so we're going to look at all these compounds and determine whether or not they are aromatic.